So, dear colleagues, if you don't mind, I think we can start. So it's my pleasure to introduce you our today's speaker, Dr. Stanislav Sergeev, LTS2 Acoustic Group, EPFL, Switzerland. And the talk is ultra-broadband sound control with deep-subwavelength plasmacoustic metalayers. So, Stanislav, the stage is yours, up to 1 hour. You are welcome. And one more question. Could we ask questions during your talk, or you wish to answer after your talk?
If you don't expect many more people to join, that maybe we can go freely through the presentation. You are free to ask the questions during the talk in Russian and English, whatever you prefer. French is somebody likes, it's also fine. So yeah, you can put the questions right away. I guess it's not a problem. The talk itself will take around 30 to 35 minutes, maybe 40 minutes. So we'll anyway have enough time to discuss things after.
Great. So you are welcome, please.
Thank you. Thanks for inviting to give the seminar. Спасибо за приглашение. Yeah, my name is Stanislav, and I will talk about the application of the plasma-based electroacoustic transducers to the control of sound. I'm working as a postdoctoral researcher at EPFL Polytechnical School in Lausanne, Switzerland, and my thesis supervisor was Hervé Lesec, and we're also collaborating with another laboratory of wave engineering, with the head being Roma Fleury. So the name, as you can see, is a little bit complex and slightly shows off, but that's the trade you need to pay to publish in some of the journals, like Nature portfolio journals. But basically, the name is, we're using metalayers, the word metalayer, because that's the, we will use a really thin layer of air, which is activated by plasma, which has some meta properties. That's why it's a metalayer. And plasmacoustic, because we have an interaction between plasma and acoustic, and this word was free to use, and we just use that. The rest, I think you can understand clearly. So I will not talk that much about the acoustics. Maybe I think it will be more interesting for you to listen about maybe a little bit the motivation and actually the plasma transducers themselves, how they operate, and what are the sound sources inside. And then, yeah, we'll finish with the examples of the sound control that we perform with these materials. So let's start with the introduction. Here I put this funny picture because that was actually the topic of the beginning of my PhD. I came here to start my PhD on the project which was devoted to noise reduction in the aircraft engines. It was a Horizon 2020 project, which was called ARTEM, and there were a lot of international participants, and our colleagues from Tsagi Zhukovsky were kindly calling this project ARTEM. But yeah, this number of projects devoted to the noise reduction from machinery highlight that there is a real problem in the environmental noise, which increases over time because we have more and more machinery around us, and it's especially picky in the densely populated Europe because we have a lot of cities which are very, very much at the boundary of the airports now, or airports at the boundary of the cities. And especially aircraft noise contributes a lot to the noise issue in Europe. At least I know that because actually the price of apartments varies a lot due to this issue. And moreover, the harmful effect of the noise was established in many researches by World Health Organizations and others. And as a consequence, a lot of new strict management rules in Europe are emerging almost every year. So that's why the need to the new methods to reduce noise is always very relevant. And at the same time, the noises becomes quite difficult to tackle because the machines become way more optimized. You have not much space to install some kind of materials to reduce noise, and just the number of machines increases. So as for the noise reduction from machinery, normally the absorption methods are used, sound absorption methods. And what we mostly see in the products is they're either porous absorbers encapsulating some devices, or resonant absorbers, resonant-based absorbers. Both of them have pros and cons, and they're pretty obvious. For porous absorbers, they are broadband in nature, but to make them work at low frequencies, we need a really big chunk of the material to really make them efficient at low frequencies. So they're not very efficient in the space-limited environments. Resonant absorbers can resolve this issue. They can be very compact and operate efficiently at low frequencies, but as you may know, the main problem is the narrowband operation. Of course, there is a mix of the two, which provides you a trade-off. It's great, but as you can see, you cannot do whatever you want with these two things. Yeah, since long time, there is a very active research on the active noise reduction methods. Basically, mostly there are two concepts, active noise cancellation, that we all probably know due to noise cancellation headphones. It works great with the headphones as the simple environment, just a single little cavity compared to the wavelengths and a very deterministic paths of the signal. But this concept becomes really tricky to implement when we go to the three-dimensional environments due to non-causality of the sound propagation, due to the large number of sensors needed, and the rest complexity. So active sound absorption can be also a way to go. This is a local control where normally we use some sort of electroacoustic transducer, mostly loudspeakers, electrodynamic loudspeakers, or sometimes piezo actuators, which provides you control over its surface with some sensors around it. And it's a little bit simpler to implement. It can have a global effect. We can enlarge the bandwidth of absorption compared to the passive cases, and tune this range of absorption. But still, there are some sort of limitations with these devices, which is often compliance to the environmental conditions. If we want a lightweight structure with the array of loudspeakers, the loudspeakers are normally rather fragile. Their cellulose-made membrane cannot sustain the mechanical impact. Weight of the system is still always bigger than the passive systems, because if we use again the loudspeaker, we have a permanent magnet voice coil on every single device, and if we want to cover substantial surface, that takes a lot of weight, and still the limited bandwidth of operation. And on this, I would just use one more slide. The problem is that the speaker is still a resonator. It's a mechanical resonator. It's a suspended membrane which is moving in the magnetic field of the coil and the magnet. And to perform the sound absorption, we normally use the impedance control technique, acoustic impedance, which is the ratio of pressure and acoustic velocity. And the loudspeakers have their own passive behavior, which is dictated by the mechanical behavior of the speaker. So at high frequencies, the impedance is controlled by the mass of the membrane. At low frequencies, it is the stiffness of the suspension and closed box. And in the middle, where we have the resonance, it's the resistance of the speaker, mostly mechanical resistance. And here I just illustrate so that if we want, for example, to actually establish the absorbing condition at the normal incidence, we know that the impedance to target would be a characteristic air impedance, the product of sound celerity and air density. And this can be done, as you can see, in a given frequency range, but still around the resonance of the loudspeaker. And then at high frequencies, the curves that we target will detach. Otherwise, if we push them further with the control, we will have a problem with stability of the system. So mostly, we don't reach really the high frequency performance, and that's due to the moving mass of the loudspeaker membrane. And if we want to really enlarge the bandwidth, not use, let's say, the compromise of different loudspeakers, which are adjusted to different frequencies, but just have a single device that can cover all this frequency range, we need alternative actuator to consider. And here are just some of the objectives which would be useful, and especially in the context of this noise reduction at the aircraft engine. The system should be lightweight, because maybe it needs to fly, but on average lightweight is better. It should be mechanically robust, and it should not present probably any resonant response, because as we see, the resonators are effective around their resonance. Even if it is an active resonator, we cannot fully, let's say, unbend it and make it ultra broadband device. And it would be also great to have a flexible design, because the speakers always have the circular shape, and sometimes it's not really surface sufficient to cover some particular places with the array of speakers. So the logical thing was to find something with little mass, and there is not really much about reducing mass except going directly to the weight of the air particles. And we thought, okay, maybe if we can control it with the electric air particles with something, for example, electric field, that could be an option. And that's how the idea of the plasma-based actuator emerged. So I think to me, this introduction is rather consistent and clear, but honestly, it was not like that. So I will spend maybe 2 minutes to really explain how we get to this idea. It was, yeah, in 2018 at the beginning there, I was being interviewed to come here to do my PhD at EPFL, and I was contacted by a professor because he saw my profile, because I had some simulation background in my bachelor with dielectric barrier discharges, so called atmospheric plasma, and some experience in acoustics due to my master. And I was called by Erve Lisek, and he said, you know, we want to reduce noise with plasma. I said, sounds great, sounds really exciting, I'm coming. And I came, and I understood that the idea was that there was another professor from mechanical engineering who had a lot of colleagues from Tsagi Zhukovsky, and these people are very, very in-depth researchers for aerodynamic flow and noise and everything applications. And there is a group which works with plasma-based actuators, a specific type of the discharge that if you deploy it on the airfoil, for example, it can change the properties of the airflow rounds. Basically, you introduce a bit more momentum to the air, change the velocity, and by consequence, you can change the flow from turbulent to less turbulent, to more laminar. And you can imagine that as the consequence, laminarization of the flow leads to the noise reduction because you don't have dissipation in the laminar flow, and there is no dissipation to acoustics. So that was the idea in mind of the professor from mechanical engineering, and Erve Lisek, as the professor in acoustics, was thinking, when you excite this dielectric barrier discharge with some pulses, it makes some striking noise, which is consistent with the period of the signal you excite. So it produces some noise, maybe we can control that. So that was the idea. So they wrote a one-page application so that we will propose an innovative technology, because that was exactly the package in the project, innovative technologies to 2050. So just something new to think about for the noise reduction. And that's where I came. And I understood that for active control, you need the actuators which respond linearly to the signal. So if you have a tonal noise, you need to have a tonal output without any harmonic distortion in order to not bring more noise. Yeah, the response of the speaker of your transducer should be linear. But these dielectric barrier discharges are absolutely nonlinear in their response. It's basically a little explosion that you excite every while periodically, and it has absolutely no control over phase and not even much about the amplitude. And I thought, right, after 2 weeks of coming here, like, am I quitting right now, or I should try to struggle a little bit more? Because there was absolutely no background, no idea what to do. But yes, fortunately, the good literature review, a lot of web reading and YouTube watching helped really to establish an understanding that there is some path to go through in order to connect these two. At the beginning, I think not very connectable parts, plasma physics and acoustics, in order to produce something that can really interact in an understandable manner with acoustic field. So what I learned is that there are two types of the plasma transducers: hot plasma transducers and cold plasma transducer. Plasma transducer, I call here whatever has 2 electrodes and can initiate the discharge in between the two, because as a consequence, you will always have some acoustic response with them. So hot plasma transducers, they are represented mostly by electrical arcs, high frequency discharges to have a high density of plasma in between, or strong streamer discharges. And they can interact with the sound field, with the acoustics around, due to the deposition of heat in the region around the discharge. Here you have an example of electric arc, and you can imagine that it heats up a lot the air close to that. So it changes the density, and it can create a shock wave or sound wave which goes around due to the heat exchange. But the consequence, negative consequence of these hot plasma transducers is actually that they're hot. They're tending to destroy everything around them due to very high temperatures, and they're normally point sources. Electric arc, it's very difficult to establish on a big distance. High frequency discharges and streamers, they are also not very volumetric. And if we want to use them, for example, for sound absorption, we would like to cover some area. And that's pretty complicated with these discharges. So it was no go for further research. The second group of the plasma transducers is the so-called cold plasma transducers, and they're called cold because heat deposition is not the main sound contributor in this discharge. Mostly the interaction with the air around happens due to the directional movement of ionized particles that you establish in this plasma region and their movement in the electric field. They interact elastically with the air around them and can transfer some mechanical momentum. And as you imagine, they can change the acoustic behavior around them. And of course, there is a little bit of heat deposition, but it's not that a big problem. It's not destructible as much as in the hot plasma transducers. So their advantage is that they can be arranged over high surfaces, over larger surfaces, and be used maybe for the sound control. But as I told earlier, the dielectric barrier discharge, the photo you see here on the left, is something as the non-stationary plasma. Normally you strike very high voltage and then you have a displacement of the particles which initiates the plasma. You have tiny streamers in the between, but this is a nanosecond process that is perceived by acoustics as just a shock wave. So basically you can produce very much shock waves, very good pulse sources, but no control over its duration, nothing to be continuous, and absolutely non-linear thing actually. So, but I figured out that in the corona type of the discharge, if you can produce a very specific geometry, here you can have a continuous glow discharge, which could maybe interact in a more linear manner with the acoustic field. And that was the choice I made to continue the research, is the corona discharge type of the actuator in a specific geometry to go further. And now I will tell approximately how this actuator operates and how it interacts with the sound fields. To produce this discharge in the way we would like to, you of course need two electrodes. One of the electrodes is a very small typical dimension electrode, being thin wire, can be blade, can be needle, let's say of mostly micrometer size or millimeter size, depending on the voltage. The second electrode is something much larger. I call it collector electrode, and for the purpose of convenience, we ground it. It can be plate, it can be grid or something like that. And the distance between the two electrodes should be larger than the diameter, the typical size of the emitter of this tiny high voltage electrode. Here, at the specific voltage ranges, if we go high enough with the voltage that we apply to the emitter electrode, the electrical field locally around this electrode can become higher than the breakdown magnitude of the electric field in the air. And we can generate the local ionization process around this electrode. So we will produce all types of the particles depending on the gas that you operate. So in air, it's quite complex. You'll have a number of positive ions, some negative ions, and of course, a lot of electrons. And negative charge in this configuration will be neutralized by the positively charged emitter electrodes, but the positively charged ions will leave the ionization region and drift towards the collector electrode. This volume is called the drift region because the particles indeed drift. They don't have enough energy here in this region in order to provide further ionization. So what they do, they just interact with the neutral particles of the gas in this volume. So they transfer their momentum in the elastic interactions, and as you can imagine, they create a fan effect. They just push the air outwards. As this is the mechanical force that this type of cold actuators can produce. And this thing we can really try to control. Of course, there are a lot of non-elastic processes in this ionization region, which lead to losses, mostly into heat. And this is another tiny source of the sound in this region here. And now you can imagine that if we establish the discharge at a given voltage difference, now if we add the alternating signal, which varies in time, we can increase the voltage between the two electrodes and increase the interaction. We can increase the heat deposition, and we can increase the electric field strength here. So increase the force that the positive ions are pushing with the neutral particles. When we decrease the voltage, the particles will deaccelerate, and with this you can imagine that we can create some perturbations, and quite actually in the linear manner. So that's the idea how this corona discharge actuator can interact with the sound field. So I've built the actuator in this particular geometry, where we have an array of thin wires which are equally distant to the second electrode collector, which is a flat plate, normally perforated plate, so that we are transparent to acoustics and transparent to the airflow. And with this, we can make a distributed source, because we will initiate the discharge around every single electrode here. And the positive particles, positive ions, will be diluted in the volume between here. And we have, nicely distributed source with the velocity that we create normal to the surface of the transducer. So it could create a homogeneous flow velocity, quite homogeneous electric field in most of the volume, which can be nicely approximated analytically in a very, very simple manner, and we can interact with acoustics. This is how the transducer looks experimentally. We just made a dielectric frame over which I strung the array of wires. It's basically actually a single wire which passes many times. The distance between these two wires is smaller than the wavelengths that we operated. It can be even smaller if needed. And the collector electrode here is the perforated steel plate. So if you apply the voltage difference between these two electrodes, you will have no discharge, you will have no current between the two up to a given voltage, which is called the onset voltage or ignition voltage of the discharge. And after that, we have progressively increasing current with the applied voltage. So you see, it's a little bit non-linear relationship between the two. It follows the Townsend formula. And if we push the applied voltage too much towards the high region, the electric field strength, you can imagine, can become too strong that we will just short the two electrodes. We will have an electrical arc between the two electrodes, and the transducer will burn. So this is the high voltage limit of our operation, and this is the low voltage limit of our operation, because we don't have any discharge. We cannot ionize particles. We cannot actually then interact with acoustics. So what we need to do is to bias the transducer somewhere in the middle and establish the fluctuation in some relatively small voltage range, which you can see can be quite a linear operation in this frequency range. Approximation of this voltage current characteristics by the Townsend formula is very useful later for the model. So now, if we try to understand analytically what's going on, we write the governing equations of the sound field around. This is the continuity equation, Newton fields equation with the force that we established from the discharge, the energy conservation with heat deposition from the discharge region, and the gas equation with adiabatic expansion approximations. So from this, we can get the wave equation, and then we can solve it, for example, for free field, as I show here, for two different sources inside the discharge. I call it force source and heat source. But to really know the amplitude of these things, we need to know what is the integrated contribution from the heat and from the force. And this is how I approximate. It's pretty simple. With the heat source, it's really easy. I just say that we a bit overestimate the source. We say that all Joule losses in the discharge are going to the heat, and it's the heat power from the electrical operation of the discharge, and then we exchange the current by this Townsend formula, and we can have an approximation of the heat source only through the voltages. With the force, it's a Coulomb force or Lorentz force, the same thing, acting on the ions. So we just use the charge density as the variable here, but in this simple geometry that I made, it can all be just integrated through the quite similar and homogeneous electric field over, and you use just the total current through the discharge as the parameter to know in order to actually calculate the total force. So it can also be represented through the voltages applied to the discharge. So that's how we approximate the heat source and force source in the discharge in order to calculate its contribution to the acoustic field around. So now I'll just tell what is the how we interact with the acoustic field. I think you already guessed. It's quite simple. If we don't have any discharge, you saw that the transducer is pretty transparent to sound. Yeah, we could measure the transmission losses. They are really negligible up to kilohertz range because the perforated plate has enough porosity in order to propagate sound freely through that. So here we have our transducer, the grid, and the wire, the high voltage wires. And if the sound wave comes to the discharge, it can freely propagate through that. And if the transducer is enclosed with the rigid wall, the wave will reflect without no losses and propagate back. So the idea is here to actually control these force and heat sources in the wise manner in order to add them to the total sound field and create the control over this incident wave in the manner we want, as to absorb sound or do something else. This is the control system that we are using. It's also fairly simple. I use a single microphone which reads the total sound pressure in front of the transducer. It serves as an input to the control system, which is a filter based on the model of the transducer, and the output is the voltage that we apply to the electrical system. So here I just remind what are the sound sources and how they are estimated in the discharge. The main idea is that the total sound pressure that we're measuring in the microphone is the sum of the sources. It's the sum of the noise wave, sound wave that we want to work with, and the sources from the discharge region here, heat source and force source. We want to, for example, absorb sound or interact with it through impedance control. So we want to establish the impedance condition at this position, which is the ratio of total pressure to the total total particle velocity at the microphone position. So this we know. And for example, at the normal incidence, if we want to absorb sound, we need this target impedance to be equal to the characteristic air impedance. And we also know what will be the passive behavior of the discharge. Of the discharge itself, it's nothing, it's just a piece of air. It will be just the enclosure. The rigid enclosure or not fully rigid enclosure, and its response at the distance x from it. It can be measured, it can be estimated analytically, we will see further. So from this set of equations, we can generate the control transfer function, which will be the ratio of the voltage, alternating voltage we want to apply to the transducers, to the input sound pressure that we are reading with the microphone. And here is this ugly equation that is the control transfer function. This is the analytical equation. It has a lot of exponentials, a lot of tangents, everything that is hated by the control systems. So to implement it here, we need to convert this thing to the rational polynomial with the Laplace variables, g omega here, yes. And basically what I did is just the low frequency approximation, but high enough in frequency so that we are good, of the exponential and all the tangents. And we can see that, yes, the analytical expression would be the the blue curve, and the one that I achieve is the red curve here. It has very good match in the magnitude, but not that good match in phase. But luckily, I made it in a way that it has a phase lit. And since any control system has delay in the controller, we can tailor this delay in order to actually try to match the phase better. And we can see that this is the region where the phase will fall if you have a delay in the controller from 0 to 80 microseconds. So yeah, I did a little bit of simulations to understand what would be the really good delay. And here it's just another graph in terms of achieved impedance and achieved absorption coefficient that you can get if you implement directly the controller that I established with no delay and with delay up to 80 microseconds. So we can see that with no delay, the absorption coefficient is still respectable, should be still respectable up to 2 kilohertz. And then if we increase the delay, this thing can be lifted and then it will fall again. And at 80 microseconds, this is this red curve that is again around the performance of the curve with no delay. So here it's the case of normal incidence absorption with the target pins of characteristics area impedance. Here it's a third graph, which is representing exactly the same thing. The simulation results where you vary the control delay in order to see what kind of absorption coefficient you will achieve. And yeah, from here you can see that in order to have maybe maximum out of the maximum, you can try to target the delay of the controller, the total one being 50 microseconds. If you want to push absorption to high frequencies, maybe you can try to introduce a bit higher delay. If you want to have a little bit higher absorption to low frequencies, but it's anyway higher than 99%, don't really care. You can make a smaller delay. So I implemented this control system on our hardware and measured the results in the impedance tube. I used two microphone methods, the transfer function microphone method, in order to measure in the impedance tube the impedance and achieve the absorption of this termination. And the termination is our enclosed corona discharge actuator, which has a single input microphone controller. Then we add to it the bias voltage and amplify everything so that this thing works to produce the absorbing condition. I had, of course, to estimate what is the minimal delay of my system, and it's already not that small. It's around 30 microseconds because we have some delay in the high voltage amplifier. We have some controller delay due to the discretization of the system. And here are the results that we get. So this is the comparison between the simulations I did and the experiments. And as you can see that when there is no discharge established, or discharge is only at just a DC mode, it has no alternating voltage applied to, the absorption coefficient is very low. It's around 0 to 0.2 because we don't have exactly rigid termination. It has a little bit of transmission through because it's a plastic termination. Probably if we made something more solid, we could have even lower, but it's fairly constant over the frequency range, and this is the impedance that we get. So we can approximate our passive behavior like that. It was measured and then put it inside the controller together with the estimation of all the sources and get the controlled responses. So here, this is the performance with the controller delay being the minimum that we can get, around 30 microseconds. And it looks quite similar to what we simulated. It's already quite high absorption up to high frequencies, but there is some roll-off due to the detachment of the phase in here. And if we try to shift the controller delay artificially a little bit higher, we can actually lift up the high frequency performance and get the absorption higher than 95% up to 2 kilohertz. That's basically it about the absorption, but you can imagine that we can have some other controls established with this type of the actuator. This is the figure that I used in the Nature Communications just to highlight what is the performance of this plasmacoustic metalayer over the frequency range and how it compares to the typical sound absorbers of the similar thickness, a couple of centimeters. So the resonator can be at low frequencies, maybe it can be tailored even to the low frequencies, but it will be limited in the frequency range. And the porous materials, they tend to absorb well at higher frequencies. Of course, there are way more advanced solutions that can make way more broadband operation, but the ones which are traditionally used in real life scenarios are something like that. And we can possibly make anything between the almost no absorbing condition and very absorbing condition, and maybe make it frequency dependent too. This is just another example that we worked with. We thought, okay, just absorption is nice, but let's try to control the phase too. And we designed a target impedance in order to kind of replicate the behavior of the transducer being enclosed, like as the enclosure was pushed further and further at larger distances. As the final performance, you can see that we try to establish the constant reflection coefficient, but we bend the phase linearly with the different slopes. And this linear phase roll will actually correspond to the constant delay, or at the same time can be imagined as the deeper enclosure of your system. So this can find a nice application, for example, active diffusers, where you need to actually mix up the sound with different delays in order to diffuse the acoustic field. So that's all about the results that we achieved with the controller. As the conclusion, I can say that the model-based, we call it feed-forward approach, because actually, yeah, we have just an established filter which operates to the input signal. It can lead to a very compact, simple solution, which can work at the large bandwidth with this corona discharge transducer. And we can not only just control the magnitude of absorption, but we can actually work with reflection, which gives you more versatility. You can control both magnitude and phase, so you can implement whatever is stable as the real-time control transfer function. And of course, the new approaches, they have a lot of consequences, and there is a huge number of them with this transducer. And basically, it's the type of the controller, but here it's not just the first one is not linked just to the transducer itself, but to all the control system. If you have a feed-forward control system, it cannot be adaptable in real time to the new conditions. For example, you change the temperature of the system, you change the humidity, the plasma will be different, and it means that it will not respond the way that you estimated it, and a different control strategy may be used in this case in order to get your response in different environmental conditions. The sound pressure level of the operation is not that big, because yes, efficiency of converting plasma into sound is not as good as with the electrodynamic loudspeakers. Currently, we are working with the levels around 90 decibels and at the control microphone, so around 1 Pascal of sound pressure, which is not that small, but not huge, and especially not enough for the aircraft engine. We need maybe 100 times more for that. And there are other limitations, which is high voltage amplification of the signal. That this is, to be fair, a real pain in the control, because imagine we want to have a distributed control system. We want to have a lot of transducers, a lot of high voltage amplifiers, and if you have ever looked for the prices of the laboratory amplifiers, it can kill the lab, any lab of any size, because the prices of the amplifier are crazy. They're huge, they're heavy, and yeah, there is no really industrial solution in here. That's a little bit of a problem, and they're not ideal in the frequency response either. There is also danger to transition to the arc if you push the transducer to too high voltages. So you really need to be in these limits. And as any atmospheric plasma, the ionization process also produces a lot of subproducts like ozone and oxides, different oxides like nitrogen oxides in the air, which are not the best thing to breathe with. So yeah, you need to protect yourself with these kind of things. But anyway, it's a very interesting device to work with, because it can really provide you way different possibilities compared to what we have before. So thank you for your attention. Спасибо за внимание, and now we can discuss anything you would like to. I think that's it about my presentation.
Great, Stanislav, thank you very much. Dear colleagues, do you have any questions, please? You are welcome.
Hi, so Dr. Sergeev, I have a question about your experimental setup for this device. So in terms of the feedback microphone's device position, so is it is there some optimal distance between your microphone? I mean, this is PT. So this is it an optimized distance between your microphone and then your transducer? I mean, this kind of a yellow plate.
Yeah, I see. Yeah, yellow region is just the, let's say, the plasma region, that the distance between the two electrodes. You need to take into account the position of the microphone in this feed-forward system. Normally, when things are closer together, you have a lower delay of physical propagation of the sound between the two things, between the microphone and your transducer, and between the transducer and the microphone. And this needs to be taken into account. If you have too far distance between the two things, it's a non-local control, and most often it leads to the instability. Maybe in the very guided case, like in the tube, it can work fine. But I would say if you want to put the microphone too far away, you better use some other strategies, which I using reference microphones to actually have to prepare the filter based on some sort of feedback or something in order to reduce sound. If you use the feed-forward strategies, which are working on the base of your reading the signal and you need to respond right away, you better opt for closest distance, because there you will have more possibility actually to make it work at higher frequencies, because otherwise the big distance between the two things will always lead to the fast roll-off, fast change in the phases, and the control systems don't like that. And if you want to control precisely high frequencies, better to keep things closer. Otherwise, it will be really tricky. You change a little bit your controller, and over this distance at high frequencies, you'll have a big shift in phase. And yeah, basically, the closer you are, the smaller your system is, the easier it is to really work with phase. So I would say optimum is really to have it close, but don't put it inside the plasma. The transducer will, the microphone will break. So that's also a limit. Yes.
Okay. So I see. So you mentioned about the delay, right? So in this slides, so the controller delay is about 18
microseconds. Yeah.
Microseconds.
Yeah.
So HV amplifier is about 40 microseconds. So how about the response time of your actuator? I mean, this kind of like a plasma acoustic device.
The actuator itself is really fast. I maybe let me have a look. I maybe have a slide on that. That's the thing. You can push further your control system to make things work even at high frequencies, because the actuator has really nothing comparable in terms of the response delay compared to the loudspeaker and compared to the system, to the control system. So here it's just a simple experiment, having electrodynamic transducer, just a normal loudspeaker, and the corona discharge actuator. When you apply this signal to the two, you see this is the voltage signal that I sent to the two transducers, and this is the signal in acoustics that I read with the microphone, which is in front of it, and you can see the difference in the response. This is what happens with the slow inertial membrane of the loudspeaker. We try to give it a pulse, but it has something vague, jelly, that's being established. You have a little bit of a pulse here and a little bit of a pulse here, but the membrane really doesn't have time to respond that fast to this kind of transitions. It is fine if it has sinusoidal response up to some frequencies, but if you really want to give a pulse, or you have a, I don't know, explosion, and you want to absorb the explosion, you really need something way faster. And here you can see this is the response on the microphone from the corona discharge actuator that is being fed with this with this pulse. Basically, you just lift up the voltage. It has a first pulse super fast, and that's how it was registered. And then you drop the voltage. So you just change change the level from high voltage to a bit lower voltage. And then it has another pulse, negative, which is logical because you had some velocity which is increased, and now you deaccelerate the ions and you create a negative pressure wave. And you can see how fast this thing is. So this comparison really makes it clear that the transducer has way more capability in terms of response speed, response delay compared to the loudspeaker. So if you want to control towards higher frequencies, you have different limitations. For example, I don't know, the size of the transducer is also another thing to consider, but you are most limited by control system, not by the physical transducer itself.
Okay, so that means so this kind of actuator, in terms of their response speed, is much faster than the mechanical speakers.
Yeah, right? You can imagine that, because to accelerate anything, you always have the Newton's law which counts, right? To give a certain speed to the mass, you have a time of accelerating this mass from zero velocity to a given one. And the lower this mass is, the faster you can accelerate. Here we are kind of at the limit. We are working with the mass of air particle, of the ions, because when you ionize the air, you don't change the mass of the system. You have the same mass as the air particle, but just without electron. We work with positive ions. So I don't see really where you can go faster with that. If you work with the air, you now have your limit is inertia of air, or other things.
Okay, so have you measured the cutoff frequency for this plasma acoustic transducer? I mean, the highest frequency.
No, because we don't have ultrasound equipment. it goes way faster, way further. And I even found, if you Google like corona discharge sound, there are actually works. This thing was really researched, studied long time ago, but just the control systems, they didn't exist, and it was not actually for control, but for generating the high frequencies. And I found a very interesting paper from some French, maybe it's in French actually, I don't remember, from a French researcher who was trying to interact with mice and dolphins. And he was using corona discharge because this thing can generate the ultrasounds that these animals are sensitive to. So I think if you try to design your own geometry, you can really go to very, very high frequencies. The problem is that the amplifier, the high voltage amplifier, will not support that frequency. You can have some pulsed amplifiers which will try to do something, but it's mostly then there will be a hardware problem again. But I think the resonance frequency of this thing should be somewhere in far hundreds of kilohertz that you will not reach with the amplification of the signal.
Okay. So sorry, I have one more question. Is in terms of electric to acoustic transfer efficiency, do you have some estimation for this kind of transducer efficiency?
Yeah, you can actually maybe get an idea from, let's say, this graph. Yeah, that I think this is exactly this 5x5 actuator, which measures the which is measured with its voltage and current curve. And I see that in the chat there was a question, probably. Let me just have a look quickly, because I think it was also about the power. But what's about the power? How much did your experimental setup approximately spend power, for example? Right. Experimental setups spend a lot of power because most of the power is on the inefficient high voltage amplifier. But this is the consumption of the transducer itself, which is also not that small. You can see that at 8 kilovolts, for example, you can have at 8 kilovolts DC voltage, you have a current consumption of around 0.3 milliamperes. So you multiply the two. The DC power consumption is around what, 2.5 watts. And I would say it's around 5 times less efficient than the loudspeaker of the same size that can produce the sound, even a bit higher in the sound pressure level. I think we estimated it's between 3 and 7 times less efficient in terms of conversion of the electrical energy towards acoustic energy between electrodynamic speaker, which is we think it's the most optimal thing, and the transducer itself. But yeah, otherwise, on top of it, we have losses in the amplifier. Yes, because so far it's the biggest engineering problem for us to really kind of design this kind of this thing. But yes, it's less efficient, and I would say it's up to an order of magnitude, probably less, 3 to 7 times, I would say, less efficient than the loudspeaker of equivalent parameters.
Okay, I see. So in terms of the active control method, so that is a general question. That is comments for this field. So currently, you actually put this one in a tube, right? So, but in a real application, we want to deal with the wavefront. So that is a real object. You want to cancel the noise. So in terms of that, is it still available to use this kind of method to deal with some like abnormal shape of the of some surface you attach to some surface, you want to cancel the noise, but if it is like a relatively complex shape, so is it possible to deal with that?
So there is a little misconception, I would say. These are two different things: cancellation and absorption. Or impedance control. It's principally different. With this device, you can control the system at the level of the interface of the transducer with the external sound field. So whatever comes to it, you can control it, and you can establish the impedance over it. Then there is a question: what would be the optimal control target in order to work in a given sound field? In the tube, it's very simple. I agree. In the 3D field, for example, where this thing can be used is you put the transducer in the corners of I don't know 3D environment where the sound pressure concentration is the highest, and you try to actually absorb the energy there. You can reduce the energy from the corners, which will have a global effect on the whole environment, on the I don't know, on a small room or something, and you will not cancel noise. You will reduce it by changing the boundary conditions of your room towards more anechoic, for example. But if you know the anechoic chamber is not a silent chamber. These are two different things. Anechoic chamber is the one that doesn't have reflection, and that's what you can establish with the plasma transducer if you cover the surface around. So I saw also after this Nature Communication paper, there was a lot of press releases after here in Europe, and people see that yes, this thing can actually make the world silent. No, it's not. It can absorb sound. It can maybe cancel out the sound, but that was not the purpose and the topic of research. This transducer was used for impedance control and absorption. So whatever the sound wave, whatever sound wave is coming, it can be in 3D field, it can be spherical wave, but anyway, it will be wavefront at the interface of the transducer. And if you estimate it with the microphone, you can deal with it. So it anyway works, but it works at the level of the interface. And then you can think how you can position these devices, if you have several of them, for example, to establish the global control effect. But it's not a pressure, it's not an active noise cancellation device, it's different.
Oh, so you mean this plasmonic layer is actually the absorption of the sound?
Right.
Right. But,
yes,
but where's the energy?
Yes,
where's the energy go? Yeah, but where's the energy go? So it
goes into control
transferred
system.
to P.
Yeah, there is a real transfer. I mean, you can think of this way. Maybe I can give you an example. It will be easier. So wait a second. I can give you an example on the loudspeaker, for example. It will be easier for you to understand. Because yeah, I understand that pressure cancellation is a very easy example. You just make acoustic pressure equal to 0, and then this thing just doesn't is silent at this position. So I will just take an example of the loudspeaker. For example, you have here a small loudspeaker. It is a diaphragm, and you know how the loudspeaker works, right? You apply the voltage signal or current signal to the terminals of the loudspeaker here. Then it passes the current through the magnetic copper coil inside, which is aligned with the constant magnet. If you apply the alternating current to the system, it will create the force in the constant magnetic field, will apply force to the membrane, and membrane will move, it will radiate sound, right? This thing is reciprocal. You can do the opposite. You take the membrane and you shake it, or you have a sound and it has a small but still very, very noticeable and registerable effect on the movement of the membrane. The membrane will move the coil which is attached to the membrane. This coil will move in the constant magnetic field and will generate the currents inside. And these currents will go somewhere else. For example, if you connect the resistor here, it will dissipate. So this is the energy transfer from acoustics to the electrical system through the loudspeaker. And the same thing happens with the plasma transistor, but a little bit differently. You don't have mechanical part. When you have an electric field, you have electrified particles, ions. And when you have a incidence sound field, this sound field will still have an AC, so alternating effect on the ions. They have their own electric field where they move, but everything sums up. You have an incident sound wave which will shake them a little bit, and this shaking will induce the alternating current between the two electrodes. And this alternating current can go in your control system and dissipate on the resistors on your amplifier. So there is an energy transfer there. Here, I hope you understand. So you have electrical system there. You see, we have ions. They carry the charge, and when these ions move between the two electrodes which are charged, they induce the currents on the electrodes, and that's where you have the transfer of energy. There is a real transfer of energy from acoustics directly to the electrical system. Here with loudspeaker, I agree, it's a little bit more clear. You have a mechanical system, which is the interface in between the two, but the principle is the same. You induce electrical signals.
Okay. So in terms of the how about the thermoacoustic transducer? So in terms of that, we know about that. We can actually use that to generate heat and then to generate sound, right? So is the thermoacoustic transducer have similar effect as the plasmonic acoustic transducers?
You say if there are any other acoustic
thermoacoustic, yes, thermoacoustic, because they can there's some techniques they use in thermal, which is they
sorry, thermoacoustic. Yeah. Sorry, I understood. Yeah, thermoacoustic. Yes, but it's a little bit tricky to work with them. I think it's difficult to let's say establish them over a large surface. Maybe you can, and you'll have the similar thing. I saw this kind of things in France, I think in another acoustic laboratory, but yeah, it's a way to go. You just need to establish way of interacting with sound field. You can use a thermoacoustic transistor too. It can possibly also be used as the device, and probably if we think a bit further, we can find a way how it can also absorb sound. There will be a transfer. Okay. So I see there is also a question from Sergey. Sergey, you can also get your question, and I will try to respond.
Okay, hello. Great. Yeah, thank you very much. Yeah.
No worries.
Sergey, can you hear us? Sergey, looks like not.
Maybe, yeah, maybe he thought it's not till 9, and then everything stops.
Stanislav, maybe I didn't get, but please clarify once again. How does the distance between wires and collector affects to the wave, to the transmitting wave?
How does it generate sound in general?
Yeah, how does this influence for the sound generation? The distance between wires and collector. Yeah, you choose 6 millimeters, but why 6? Why not 3?
Yeah,
why not 10?
Yeah. You can choose 10, but you will need high voltages to actually imagine this as a capacitor, right? You have 2 plates, right? And they can be also at a different distance. And for example, if you have a big distance capacitor, you give a voltage difference to it, 10 volts, right? It will have an electric field of 10 volts divided by 10 centimeters, right? flat, constant electric field. If you make the distance smaller, 1 centimeter, you give the same 10 volts difference, the electric field inside will be 10 times higher. Is it true? It is true, because you divide by distance. And electric field is the thing that generates, that provides the ionization, that provides the ions. Basically, the closer you put the distance between the two electrodes, the lower voltage will be for initiating the plasma, because the electric field is higher due to the smaller distance. At the same voltage difference, you can have higher electric fields, so stronger ionization, or just the thing working. If I was using, so here you see that for 6 millimeters, this is the voltage current curve. It worked approximately at 8 kilovolts. And if you put 10 millimeters distance, it will work towards 11, 12 kilovolts bias in order to have some current, some ionization to work with. So it's just the matter of when the transducer actually initiates itself, when it starts producing plasma. It's the matter of value magnitude of electric field inside. So the smaller the distance is, the better it is in general. But if the distance is too small, let's say 1 millimeter, then the discharge will be pretty unstable, because you really need to have this separation between the two electrodes, and you will not have that much volume to control between the two in this drift region. So let's say there is an optimal, but in general, I would say bigger distances is better. But then it will be difficult to find the amplifier which can actually provide this value of voltage, and on top of it also alternating thing, because that's a big problem, because DC voltage amplifiers, DC high voltage sources is not a problem to find. You have them everywhere, even in old electronic tube TVs. They work up to 30 kilovolts. But what we need is from this high voltage amplifier also good acoustic response. It needs to, if you have 30 kilovolt bias, and on top of it you send a 1 kilovolt AC wave, it should sine wave.
It's a problem. I understand.
It should generate a sine wave at the output, and that's not easy with the high voltage, to be honest.
Yeah, thanks. I think Sergey asked in chat.
Right, I see him.
No,
I mean, the host is not allowing participants to
I'm
unmute
not allowed
themselves.
to know them. Sorry, Sergey, we do not host here.
Who's
all of
hosting
us
here?
Nobody. It's
really? Okay, that's weird. But how did Yangu manage to talk to us?
Really, I don't know. I think all of us can, except Sergey.
That's a shame, Sergey. Sorry. Sorry for that.
So Sergey asked.
Yes, I'm reading. Yes, I'm reading. Am I right that absorption does not strongly depend on the angle of incidence? So it's a bit easier to talk about the impedance here. So absorption is the consequence of the acoustic impedance that you establish at the surface. And acoustic impedance has two variables inside it: the ratio of pressure and velocity. Pressure has no direction, right? It's just the pressure, and at this point it acts with the given force in all the directions. What has the direction is velocity. Velocity moves the particles. It's the movement of the particles in a given direction. As you can see, our transducer only works in a single direction. It has such an electrode arrangement which will push the electron, the air in a given direction. Here is perpendicular to the collector electrode. And what we can control is only normal impedance, because it's normal velocity, normal to the electrode. And if everything normal, like in a tube, you can control the absorption. If you have a 3D field, or if you manage to make the device which has a given incidence, then you will be able to only control the velocity, which has a normal component to that. So then you need to actually think what would be the proper impedance to estimate in order to have absorption. But basically, we can absorb only normal parts of the wave. If you try to make a trick and find out that there is an impedance value or something else, another strategy that can finally lead to high absorption, that's great. Because, for example, Stefan Elliott, if you know the person, but he's mostly in active control, but he did a lot of work in absorption. You can have some global strategies to minimize the total radiated power by absorption, or to maximize its own absorption. It can lead to maybe some different impedance targets. But here, yeah, we really work with mostly normal incidence absorption. So if you have a grazing incidence, it will still work because you have pressure, you will still have some movement there, but it will not absorb in the same way as at the normal incidence. So it kind of depends on the angle. We absorb the normal parts of the wave. And the second question I don't see yet. You also told that to increase the frequency of the absorption, the control delay should be increased. Is it correct? If yes, could you explain a bit why frequency depends on the delay? Yeah, it was maybe a little bit misleading. That what I did here, I had. Do you still see my slides? Sorry.
No.
You don't see my slides.
No, yes, we can see it.
You see my slides, right?
Mm-hmm.
So what I do here is that I have the microphone at the given position, and I established through just the equations what should be the response of the transducer in order to absorb this incident wave. And I solved the system, and it gave this long equation. And this equation is a complex. It's a complex valued function which has magnitude and it has its phase. And this is a blue curve here. And in order to really absorb sound, you need to follow this curve. You need to try to implement on your hardware the system, the function, the filter that will have total response from the microphone to the output of the transducer following this curve. And as you could see, that I know that with my amplifier I can follow the magnitude well, and I can follow magnitude well with my controller, but they have delays inside, and it means that they will have an impact on the phase of the total function that I'm establishing in this relationship. And as you could see, that the one that I'm implementing, because this polynomial can be implemented with on the control system directly, just discretized and be implemented, and it will have this shape. It will just, you see, not coincide with the phase that we would like to have at this frequency. And here, just in this particular case, we needed to add delay, for example, in order to bend this phase towards the one that should be there. But for example, if you have a very old and very slow control system, it will have its own delay already too high, and the final transfer function to establish will be somewhere already below. And it means that, okay, you will never achieve with the system the good absorption because your control system is too slow. It's just that you solve mathematical equation, you get the complex valued function, which has given magnitude and given phase to be implemented in reality, and you need to try to make it. That's why I was talking about delay, because it was a little bit tricky to go to higher frequencies in order to really match things. But with just simple delay, we could do that. We could also go a bit differently. We could try to actually fit the given function directly with a higher order controller. It would also maybe work. But that's why we talked about the delay. It's just not it's not the physics, I would say. It's just the implementation problem. In physics, we are getting directly what we need to have through the equation if we believe that our analytical estimation is correct, and that's it. We try to make it possible in real life with our means. I hope that answers your question.
Yeah, looks like, yeah. So, dear colleagues, anybody else? Nobody? So let us say thanks to Stanislav. Thank you very much. Very interesting talk.
Thank you for inviting. Yes, no problem. Always happy to give a talk.